Welcome back to Essential Perturbation Theory and Asymptotic Analysis. Today we'll finish, I hope, Chapter 3. Chapter 3 is all about asymptotic expansions of integrals. So we covered integration by parts, the Laplace method, which was broken up into two parts. We did that for Laplace integrals of the first kind and second kind. And now we're going to discuss another method for obtaining asymptotic approximations for integrals of a slightly different type called the method of stationary phase. Before I get started, are there any questions about anything? Homework, LaTeX, otherwise? Sure.
So I understand why do we need to do perturbation method for like differential equation, but for this kind of asymptotic expansion for integral, like is there any like particular usage that is useful?
Yes. So, well, for example, today we'll discuss something called the Bessel functions, and the question is what's the use of studying asymptotic expansions for things other than differential equations? So the Bessel functions are solutions to differential equations. So the way you can view these integral equations or these integrals are as solutions to differential equations in some respect. In the simplest case, just as a Bessel function solves a certain differential equation, we're going to be essentially investigating solutions of these differential equations, which are represented through integrals. So that's the first answer. Then, other special functions like the ones we've been looking at, like the exponential function, the gamma function, the Bessel functions, and things like this, are only expressed as integrals. And there's no closed form solutions to these things. And so people often want to know what is the large scale behavior, or maybe the small scale behavior, or in other words, what is the behavior of these functions as a parameter gets smaller or larger, right? So that's why they're important to investigate. So, and if you study physics, you'll see Bessel functions popping up everywhere, and a Bessel function of the first and second kind. Math students don't always see all these things that physicists and engineers work with all the time, but they come up in all kinds of applications. All right, so today, as I said, we're going to discuss the method of stationary phase. And this is for integrals which have oscillatory kernels or oscillatory parts. So let's have a look. Well, before I get into the general form or the general things that we want to study, the first thing I'm going to talk about is basic integrals of this type, where we're integrating from or on a finite interval a to b of a function, which is a continuous function, against the cosine, where cosine is cosine kx, and we're going to send k, the wave number, to be to infinity. All right. So in this case, for this, for this very special case where f is some sort of really well-behaved function, and the argument for the cosine and the sine as well is just linear in the variable k and x. Then we're going to find as k gets larger and larger, this integral tends to 0. So this is a very well-known famous result called the Riemann-Lebesgue lemma that students of analysis see all the time. But physicists are quite aware of these phenomena as well, because they deal with wave phenomena a lot. And so I'll show you in a picture where this comes up all the time momentarily. But the first thing I want to do before we motivate what's really happening here, let's try to prove this. Okay, and again, like with many of our proofs, it's not so much technical mathematics as it's just a bunch of computations. So we're going to figure out how to take this apart and really show what's happening here. Now, of course, and from a certain point of view, you can see what's happening, right? So we have a function from A to B. And one part of that function can be thought of as basically the amplitude. That could be F. So here's F. So I have to write the amplitude on the top and the bottom. So pretend like that's a perfect mirror image of F. And F for this problem is we're going to consider F to be a positive function. Okay, not have any zeros. So what does cosine kx look like? And especially as k gets larger and larger. So this starts oscillating more and more rapidly. Between its upper amplitude envelope and its lower amplitude envelope. The wavelength is supposed to be more or less the same. But as k gets larger and larger, what happens? Something like that is happening, right? As k gets larger and larger. And the argument here is kind of a heuristic argument is whatever I create on this upper side, I'm going to create something on the lower side as well that in the integral gets canceled out. These oscillations sort of cancel each other. Okay. Now you can see this is pretty obvious. If this was a flat amplitude, right, then this makes a lot of sense. I can perfectly well see how something on the top is kind of canceled with something on the bottom. And especially as k gets larger and larger, there's always going to be, I'll always be able to pair these things up so that this thing cancels with that thing on the top and bottom, and you won't create any sort of residual. So that's the basic idea, what's going on. So let's prove this. So we only have to prove the first result because the second one is going to be more or less the same thing. Okay, remember cosine is just a shifted sine wave. So if f is continuous on an interval, what do we know about that function? Well, first of all, it's an integrable function. Every continuous function can be integrated, right? This is just some value, some finite value. But now you remember or probably have this faint recollection of dealing with or looking at integrals for the very first time, and they may have been motivated to you through something called Riemann sum, right? So how many of you vaguely remember talking or hearing about Riemann sums when you were much, much younger, right? Well, we can show that if f is a continuous function, it's a Riemann integrable function. And that means we can show that there's a Riemann sum where the Riemann sum pillars are all under f. Okay, so here's what I'm talking about. Integrate from A to B, and we've got these little pillars which we can make come up and touch the function f, but we're not going to exceed f. We're just going to touch it and stay under it with those pillars. Okay, so basically you push the pillar up until it just touches that curve. No, this is not a good one right here. Now, intuitively, what do you know about the Riemann sum that's generated by summing all these little pillars?
It's less than
Yeah, it should be less than f, right? So another way of saying this is I can find a step function. So the step function is this object, okay? Step function is defined as a summation of a bunch of little pillars. That's what these things are. These are the pillars. This is what's called a characteristic function. The characteristic function turns on when it's in this interval and it's off otherwise. So it's 1 whenever it's in this interval and it's off otherwise. So in this interval, it says that the value of this step function is just going to be ci. And my interval here is going to be, that I'm talking about, is I to, let's see, I minus 1 to I to, sorry, the ith interval is I minus 1 to I. Now, this, of course, is defined by what's called a partition. Remember Riemann partition? You'd partition up A to B in a bunch of little pieces. That's a partition. And so I can create this step function subordinate to this partition. And I know that I can find a step function which fits nicely underneath this continuous function f. In fact, I can tell you exactly how to find it. On each little subinterval, I minus 1 to I, xi, I can just define ci to be the minimum of f on that interval. I can just define it that way. Okay? And that's going to describe exactly what I want here. The pillars come up and they touch f, but they don't exceed f. And so I know that I can find, because this f is Riemann integrable, remember I can find a fine enough partition. I can find a fine enough partition so that the difference of the integral of f and the difference in the integral of that step function, remember the step function is underneath of f. When I integrate this difference, I get something which is less than any epsilon that I choose. And I'm going to choose epsilon to be epsilon over 2 here. So here's the way it reads. There exists a partition and a step function given any epsilon such that that step function fits under f, okay, snugs up under f, and the difference between the integral of f and the integral of g, the step function, is less than epsilon over 2. Okay? And in fact, I know how I can choose this step function in a simple way. In fact, I can make the partition to be a uniform partition. I don't have to get anything exotic here. All right, so if you believe that, then I'm going to use this function g in an advantageous way. Remember, g is a good approximation for f, at least in terms of its Riemann integral. So I'm going to add and subtract g. What happens when I add and subtract g? I'm really just adding 0, so I'm not changing anything. I'm doing it inside here in against f. So I'm putting parentheses here against f, and I'm adding and subtracting g, so I'm not changing anything. I'm taking the absolute value of this integral. That's fine, I'm allowed to do that. But I still have equality up to this point, not changing anything. Okay, now what do I want to do next? Well, remember the integral is something, it has a property that we call linearity. And what that says is that if I integrate two functions, h, and I want to use something else here, h of x, t of x, from a to b, then this is equal to the integral from a to b of h of x plus the integral from a to b of t of x. Okay, so I can split that integral up into two integrals. You guys remember that property? You use it every day, but you probably don't think about it. That's called the linearity property. So I'm going to break this integral into two integrals using linearity. I'm going to group them in this way. I'm going to group f minus g and cosine together, and then g and cosine as a separate integral. I can do that. And then I use what's called the triangle inequality for just the basic triangle inequality for the absolute value. So I get this line. What's the next step? The next step is I'm going to bring the absolute values inside the integral. If I do that, then I'm going to use a property of integrals, which says that if I bring an absolute value in, let's use h here. Then this is less than or equal to the integral from a to b of the absolute value of h. Do you buy that? It's a true statement, so you ought to. Okay, as long as h is a nice enough function. We're assuming it's a continuous function, so that's fine. So I'm going to bring this integral in, or this absolute value inside, and then I'm going to argue, well, this absolute value here is at most what? What's the largest the absolute value of the cosine can be? 1. So I can replace this with its largest value. And that gets me from this integral to this integral. I'm going to just replace this by 1, but that's the largest this could be, right? So I have to replace this integral with this one with a less than or equal sign. This guy I'm still bringing along for the ride just as is. Now this one I said before, G is a close cousin of F, right? It's close within epsilon over 2 in integration. So that's where I use that step. Now, finally, I want to think about what this guy is. This is just a step function, right? And I can integrate the cosine against this guy term by term in that step function. Now, on each interval where the step function is constant, then that's just going to be a regular cosine integral. So this gets replaced as integral. I'm going to interchange it, summation. Okay, so it's a sum from k equals 1 to m, right? So how many? Oh, I think I may have an error here. This should be an I, right? That should be an I. So let's change that. That's I and that's I there. Okay. Just wondering where the K popped up. K is my wave number. So there's sum I equals 1 to m. And now I can integrate over each piece of that step function. But remember, the step function is defined through these characteristic functions, which are often on. And so this really becomes xi minus 1 xi of ci. The ci can come out. And all that's left in the integral is going to be cosine kx dx. That's what happens when I replace g with what it actually is, that step function. I can replace this exactly with this. Now, this guy is exactly integrable on each one of these intervals, no problem. And when I integrate the cosine, I'm going to get sine, right? So when I swap this g out with this formula, I exactly get this. That's with equality. All right, now this should be I, of course, but this 1 over k is here, and that's because the integral of cosine kx is 1 over k sine x. And I have to evaluate at the endpoints. Now we can bring this inequality inside. Okay, so that's basically triangle inequality again. Sorry, I said inequality. We can bring this absolute value inside, and it's going to attack everything you see here, right? What's the largest this guy can be in absolute value? A sine of evaluated at some point minus a sine evaluated at another point. The largest that could be is 2, right? Because it could be 1 minus a minus 1. So this could be as large as 2. So that's why I'm going to put the 2 here. All right, so now I have this expression. That's what I just showed. So I hope you all believe that. Now, I can take k large enough so that this guy becomes small, right? Less than epsilon over 2, because I fixed my partition, right? I fixed my partition whenever I chose the epsilon here. So the partition only depends on the size of the epsilon that I want. Okay, it doesn't care about k. It's only chosen to make this small. Now, all I want to do is I want to argue that I can make k small enough or large enough, the wave number large enough, so that this whole amount becomes less than epsilon over 2. All right, now, if that's true, which it is, then I can say given any epsilon, I can make k large enough so that this integral in absolute value is less than epsilon. Actually, it's epsilon over 2 plus epsilon over 2. All right, if you tell me how small you want epsilon to be, I can choose k large enough so that this integral can be less than epsilon. So somebody give me an epsilon, your favorite small epsilon. Don't say one. 1/1,billion, right? Or 1/1,trillion.
Trillion.
A Google. Okay. Or is it a Google or Googleplex?
I think both of them.
That's right. Which one's bigger, the Googleplex? Yeah. Okay. So 1 over a Google or a Googleplex. Okay. I can give you a k value where this integral in absolute value is going to be smaller than that. So if this can be made as small as I want, what do I know about this limit as k gets large? Has to be what? Has to be tending to 0, right? It has to be tending to 0. If I can always choose it, I can make epsilon as small as I want, then I can find a k large enough so that this is an absolute value less than that. That means that the only possibility here is that the limit as k goes to infinity of this guy is 0. Okay. It's a little bit of extra little analysis, but that's what you can prove. So we showed that this limit is 0, and by the same analysis, this guy is also 0. And the proof by picture that a physicist might use is also, turns out, maybe it's not rigorous, but that's what's happening. Okay. Any questions? Yes.
If you're gonna call k a wave number, what's like the scenario where you would be letting your wave number go towards infinity?
Highly oscillatory. You're just cranking up the oscillation rate. I don't know a good physics scenario, but you have an oscilloscope and you turn you turn a dial up and it starts wiggling an awful lot. So we'll see where this comes out in the proof of the asymptotic expansion of the Bessel function. So that's one place where I can say here's where this comes. Here's where this appears in nature. All right, so that's called the Riemann-Lebesgue lemma. We can prove a generalization of that as well. So in the Riemann-Lebesgue lemma, we just assumed that f was a continuous function. What if we assume that f is a C1 function? Well, if f is C1, then we can do what's called integration by parts. All right, and so if we do integration by parts, we can show that actually this integral f against cosine kx is going to 0 as we wanted it to. In fact, it's going to 0 like order 1/k. Okay, k is getting large. So we know how fast it's going to 0. So in the Riemann-Lebesgue lemma, we don't know how fast that integral is converging to 0. In this case, we can say that it's converging to 0 like this order.
So which is quite slow.
It's not that fast, yeah. I mean, it's better than 1/k to the 1/2, right? So in fact, we're going to take advantage of the fact that this is faster than another rate of convergence that we'll deal with momentarily. So from one point of view, this is slow, and another point of view, it's fast. Everything's relative. Okay, so how do we prove this one? Again, these are proofs by calculations and by intuition, really. You have to have the right intuition, but the Riemann-Lebesgue lemma comes from the fact that you can say, well, it's a continuous function. Therefore, if I look at it on little intervals, it's looking like a constant function on little tiny intervals, and then I can send k to infinity. Here we can use what we already know about Riemann-Lebesgue and use integration by parts, and we can prove this quite quickly. So let's do one application of integration by parts. So here I'm showing that integration by parts that we studied previously can actually be used in other applications, not in exactly the same way, but it's similar. So what are we taking here? We're going to take v to be f and du to be cosine kx dx, right? And then we use our integration by parts formula. I won't write it because you guys know it by now. And so we have a boundary term, and then we have negative the integral of, what is it? It's a u dv. Okay, so now let's do some estimation. By the standard Riemann-Lebesgue lemma, we know that f is a continuous function now, right? It's a C1 function. By the way, what does a C1 function mean? I just want to remind you. We've used this notation before, but it's good to think about what it means. It means f has is a continuous function, and it has a first derivative. Okay, that first derivative exists, plus we can assume that the first derivative is also a continuous function on the same interval, closed interval. So that's what it means for f to be a C1 function. It might be better than that. It might have an infinite number of derivatives, but we're going to say f is a function that has at least this much. We call it regularity or smoothness. So we know that f prime is a continuous function on a to b. So what do we know? Riemann-Lebesgue tells us there is a k naught such that if k is bigger than k naught, then this integral can be made small. I'm going to make it smaller than 1 because that's all I need. That's not that small, right? It's not certainly not as small as 1 over a Google. So we just need to make this less than 1. Why? Because this guy is already going to be multiplied by 1 over k. All right. So if I just say I'm going to choose k large enough so that this is less than 1, then that's going to be all we need. Now, what about this term here? We can deal pretty nicely with this one, as we'll see. So let's see here. Let's take that together in pieces. Okay, so now apply absolute value to this integral and use a triangle inequality. So we're going to slap absolute value here. We can replace that with a plus, and we have an absolute value there as well. Now we just argue, how can I make this guy, how can I bound this? Well, I don't need to bound it by much. All I have to say is, well, what's the largest this difference can be? What's the largest this difference could be in absolute value? It turns out it's less than 2, because the largest the difference between a sign can be is 2. And the max of f. Okay, so I can argue it that way, that this can be less than 2 times the maximum value of the absolute value, maximum of the absolute value of x, f of x. I'll get it right one day. But I also have a 1 over k, and so when I take absolute value, that 1 over k stays itself. So that first part can be bounded in absolute value by 2 over k max absolute value of f of x over the interval a to b. Now, all of this stuff here, this and all that, is completely independent of k, right? And this, I put a 1 here because I wanted this guy to work out to be 1 over k. As long as k is large enough, then I'm going to have this integral is less than 1, and so I can show this estimate here by using the triangle inequality up here. So then my result just follows, because remember what order means. This means I can find a constant. I can find a constant such that that integral in absolute value, cosine kx dx, didn't save myself enough room, is less than a constant times 1 over k. Okay, for k small enough, there exists a constant, and the constant that I'm going to choose is just all this stuff. After extracting this 1 over k using the distributive property, then the constant that I have left would naturally be this. Does that make sense to everyone? That's the constant that I want to extract here. And this is, we say, when we can prove something like this, we say that this integral is big O of k to the minus 1 power as k goes to infinity. That's what it means. What's that?
There's a Riemann-Lebesgue
Oh, okay.
LGBT.
Ah, so one of our students asked ChatGPT to
to plot it,
prove or plot
plot.
the
But
Riemann
this
Lebesgue.
has a higher wave number,
Okay,
so it's more dense.
okay. Does it, but it all works out. I'm not lying.
I think so.
Oh, you think you think I am lying or not?
No.
Good, good. Because we just proved it, so we know it's true. Okay. We don't want to, what, I mean, ChatGPT does that say that correct things are wrong, so up is down and down is up for ChatGPT sometimes. By the way, so some have asked what's a good way to learn LaTeX? It's the best way. So ChatGPT in combination with something like Overleaf is a pretty good combination. So you can keep taking your file, and if you get an error, LaTeX editors aren't very good at telling you what the error actually is, but ChatGPT can do a lot better. So if you type something and you get an error and say, I probably missed a usually, yeah, it's a $ or a bracket, right? What kind of bracket? Well, ChatGPT is a good, it's very cooperative and can tell you where your error is. But you have to do it piece by piece. If you throw in something which is completely wrong into ChatGPT, it might not be able to tell you what your error is exactly. Okay, so right, so we proved this. So in this chapter, this section of the chapter 3, we're going to be interested in approximations of integrals of this type, which is a bit more general than the integrals that we've been working with. But we can kind of see how the integrals that we have been working with can be made into this form, something like it, or that this guy could be made into the integrals that we were talking about. Let's suppose that now we're going to use, instead of a wave number k, we'll use lambda. But how could we make this integrand look a bit like what we just had? Well, right, so f of t, you can't do anything with f of t, but e to the I lambda psi of t. If everything else is in sight real, then this is cosine lambda psi of t plus I sine lambda psi of t, right? And so when we multiply by f and integrate, then we have some integrals which look an awful lot like what we were dealing with. But the one thing that's different here is if we're treating this as the wave number, this guy may or may not be linear anymore, okay? This guy may or may not be linear in t, and so it might be a bit different than what we were dealing with. So we need to know how to handle the situations where this guy might be, this guy has some structure. Let me just put it that way. So let's look at that integral, okay? And if you do, by the way, if you integrate something which looks like this, you might say to yourself, I can't do that. I don't know how to do complex integrations. Well, you can. You just, all you do is you treat this number I as if it was just a regular real constant, and you can write the integral like this. So I of lambda AB f of t, no, t, there we go. Cosine lambda psi of t dt plus I b f t sine lambda psi of t dt. Okay, so you can just break them into two real integrals like this. We're assuming, at least for now, that this function psi is a real valued function. So we can calculate, you agree, we can calculate, or at least think about calculating an integral which looks like this. In fact, we can use integration by parts on it without any problem. Now I claim that if f is a C2 function, that means it has two derivatives. So the function and both of its two derivatives are continuous functions on the closed interval from AB into the real numbers R. By the way, I forgot to mention these guys, this second slide deck from chapter 3, I posted on Canvas right before class. So you can go grab it if you have an electronic device. But it's up there. But if you didn't see it 10 minutes before class, that's the reason I posted it maybe 5 minutes before class. And by the way, I also updated the notes. I do that more or less every time that I come into class. You'll notice that the notes will be in a state of flux until we leave a chapter, and then they sort of settles down. So chapter 2 hasn't changed much in the past few weeks. Chapter 1, not very much. And now once we emerge from chapter 3, it's not going to change very much either. So until that period of time, I definitely wouldn't think about making a permanent copy, you know, of don't go out and get it bound into a, you know, nice leather back edition until the state of it is in less flux. And again, in any case, the notes and the slide decks are now updated on Canvas. Now, so we have another generalized Riemann-Lebesgue lemma that I want to mention. This one we'll use an awful lot. So if f is a C2 function and psi is a C3 function, and I don't remember why I need C2 and C3, but I have thought about just asking you guys to do the proof. I'm going to call it a proof calculation or calculation proof, and maybe you can find out why we need that. But then I claim I can show that this integral from AB of f of t e to the I lambda, lambda's our large parameter now, psi of t dt is equal to this value. Now, where does this value come from? Well, this value here comes from our first integration by parts, right? First integration by parts using v to be f and du to be all the rest of the stuff. And so if I do that, you can see that u is just going to be this bit here. And so this is just vu evaluated at the points, the endpoints, t equals a, t equals b. Okay, so if I can calculate that first term, then I claim that the rest of the terms are going to be all order lambda to the -2 power as lambda goes to infinity. So in other words, what I can show by that is that this integral is asymptotic to this value. Now, what is this value? Well, this value here is essentially, these are all, everything's constant in sight once I do these evaluations at t equals b and a. All right, and what I'm really after here is the order. And the order comes from this guy here. So this is like an order 1 over lambda term. And I'm saying that this integral is basically 1 over lambda plus a higher order term, which, what's the higher order? It's big O of lambda to the -2 power. If I can show that, then this is the same as saying that f is asymptotic to this value, to this 1 over lambda term, okay? Again, here, once I do the evaluations at t equals a and b, then everything but this lambda becomes just constants. Now, the other thing that I need here, and I need to be careful about, is that I need to assume that phi of t, when I take the derivative, is not equal to 0 for any value of t between a and b. Okay? Now, why I need to do that is a bit technical. You might say to yourself, well, I really only need it to be non-zero at the endpoints a and b. Okay? So I'm going to let you go through the calculation and see why you may need this to be more generally true. But at least if we assume this, then we're certainly safe in saying that at the endpoints, we're not going to be dividing by 0. So that's nice. That allows us to conclude that this is really an order 1 over lambda term. So I just wanted to point that out. Now you have to use integration by parts twice. And that may be why you have to have f being a C2 function and psi being a C3 function. Again, the details are left for an exercise. Calculation proof. Yes.
I think you need the C3 because you need boundary. Or otherwise you don't have that constant that you can bound.
This guy here.
Yeah.
Well,
If
after-
the second time you have the second derivative, you bound the constant, so you need it to be C3 because if you want to bound the constant.
That may be. But I haven't thought about it in a while, so I don't know for sure. All I know is that you can see what term's going to pop out after one integration by parts. So the question is, why do I have to do integration by parts twice? It looks like maybe I'm covered with the first time, but actually doing it the second time, you should be using the fact that f has to be C2 and psi has to be C3. All right, so let me define exactly our, I wouldn't call it our enemy. I was going to say our enemy. No, our point of interest or our integral of interest in this section. So the integral that we're going to be interested in is what's called a Fourier integral. And it's exactly the thing that we just mentioned, or an integral of the thing or the type we just mentioned. We're going to relax a little bit and say that f is just a continuous function, but it can have its values being complex. And psi, we're going to assume, is a C1 function, and it's a real valued function, okay? This integral then is what we call a Fourier integral. Now, if this has a bit more structure, we're going to call that something a little bit different. So this integral is called a Fourier integral of stationary phase, if and only if there's a single isolated point T naught in AB such that psi prime of T naught is equal to 0. Okay, so this is what we call a stationary point if this happens. And I'm going to show you what the picture looks like to have a stationary point. Assuming that psi is additionally a ck plus 1 function, then the point T naught is called a point of stationary phase of order k, if and only if the derivatives at T naught are equal to 0 for all orders up to and including the kth order derivative. But when you go to the k plus first derivative, it's non-zero. Okay? So the one that we'll be mostly interested in is k equals 1. So whenever k equals 1, that means we're looking for a point where psi prime at T naught is equal to 0, but psi double prime of T naught is a constant alpha, which is non-zero. Okay? So that's the standard one. This is the standard and the most common, I think. Okay, so we're interested in these stationary phase integrals. Now, what does a stationary phase integral look like? Well, you can't maybe visualize an integral. An integral is a number, right? I guess you could visualize the value as lambda changes, the wave number changes. But let's plot two different integrands of the type that we're interested in with these Fourier integrals. Now, I'm not writing these as an exponential form. It turns out the exponential form is the simplest thing to deal with. But we could just think of, instead of the complex exponential, just sine or cosine. Like we could think about cosine of lambda psi t. Okay, so that's the idea. So let's consider these two functions here. And remember, we're looking at cosine psi or lambda psi of t. So here I'm taking psi to be the cosh of t. Okay, no problem. So would an integral that has this as its integrand be a Fourier integral of a stationary phase? Yeah, it is. We could take the real part of one which has this complex exponential, but basically you get the idea. Now, what we have to figure out is, well, is there a stationary point and what is its value and what is its order? So the stationary point for the cosh, does anybody remember what the cosh looks like? I think it looks like that, right? So it has a stationary point here, and this stationary point is the only possible one in any interval. Okay, but if the interval contains 0, as our interval will, because we're going to be interested in, I believe this interval is from minus pi to pi. Well, there's a point of stationary phase right there at t equals 0. And we can see that the derivative is 0, but the second derivative is positive. Okay, so our alpha here is positive, but otherwise this is a point of, this is a stationary phase point, or point of stationary phase of order 1. Now look what happens at a stationary phase point. Okay, there's our stationary phase point at t equals 0. Basically what's happening is the oscillations slow down and you get this sort of calm region in the midst of a storm. Away from the stationary phase point, you get a lot of oscillations. So what happens near a stationary phase point is that the oscillations slow down, things calm down, and it's kind of like a break in the storm or the eye of the storm. Now, as lambda gets larger, so let's take it from 2 is this curve here, to 4, what do we see? As lambda gets larger, the calm point stays at the same point, right? T equals 0. But outside or away from the stationary point, the oscillations get more and more rapid. Okay, so you have this point of calmness, but as lambda gets cranked up, the oscillations outside of that calm point become more and more rapid. All right, so this is how you characterize, or what it looks like to have a stationary point for these integrals. You can evaluate integrands like this, and basically this is the photograph that you would take it every time. Okay, if you zoom in on this guy. Now, this isn't all that's going on, right? Because in addition to this oscillating piece, I also have this amplitude function. But you can imagine if f is not 0 at that point of stationary phase, then basically f just looks like a nice undulating function the more I zoom in on it. Okay, it's well behaved. Okay, as long as it doesn't go through 0, then basically the picture is just going to look the same, except I'm going to have an amplitude envelope around it. All right, so let's do an example. So let's consider the Bessel function. So I'm going to use this example to basically introduce the method of stationary phase. We've already talked about the definition of a point of stationary phase, but what is this method of stationary phase? So I'm going to use this example of calculating or approximating the Bessel function to introduce this methodology. Now, we're always going to be interested in approximating integrals of this type as lambda gets larger and larger. So that's the goal. But now, this doesn't look like a stationary phase integral in the strict sense, right? Because it's not a complex exponential in here, but we can see that the difference between that and the thing that we've already defined is we can just take the real part of this object and we get this. So if we analyze this integral in here, then we'll have analyzed the asymptotic behavior of this integral that we want. That's the idea. All right, now in this case, here's our integrand, e to the I lambda sine t, and we're integrating from 0 to pi. This is very important that we recognize what are the limits of integration. Because when we're doing stationary phase theory, we can only deal so far. We're only wanting to deal with the case where it has a single point of stationary phase in the interval of integration. So the interval of an integration here is 0 to pi. So in this case, psi of t is just sine of t, which of course, 0 to pi looks like this, right? More or less. Looks like more of a half circle than the sine function, but you get the idea. So it looks like we have a point of stationary phase right in the middle at t naught equals pi over 2. The derivative is 0, and the first derivative is negative, right? It's frowny face. So our alpha is negative in this case. So t naught is a point of stationary phase of order 1. No problem there, where t naught is equal to pi over 2. So let's rewrite this integral a bit, because what we're going to find with integrals of stationary phase, that what we really need to do is zoom in on what's happening around the point of stationary phase, and everywhere else we can kind of neglect what's happening. Okay, so what I mean is, let's examine this integral. This is the integral whose real part we're going to take to get back to J0, our 0th order Bessel function. By the way, this is the 0th order Bessel function here, in case you've never seen it before. It can be defined in a couple of different ways, but a common way to define it is as an integral of this oscillatory thing in here, kind of doubly the oscillatory. All right, so we're interested in this for large values of this wave number lambda. So we're going to break this integral here into an integral which is just around the stationary phase point, pi over 2, and what we call the integral tails. So we'll always be dealing with something around the interval of interest and the tails away from that. Well, the first thing we want to take care of is the tails. Okay, what happens with the tails? Well, with the tails, notice that when we're far enough away from the stationary phase point, then the sine function doesn't have anywhere where its derivative is 0, right? And so we can use that generalized Riemann-Lebesgue theorem. As long as psi is not 0 in the modified interval, we're okay to use that. So notice sine does not have a derivative equal to 0 in this interval, 0 up to pi by 2 minus epsilon. So what we're saying is, all right, here's t naught, pi over 2, and we're backing away from this by an amount epsilon. So this is t naught minus epsilon here, and t naught plus epsilon here. In this interval, sine does not have anywhere where its first derivative is equal to 0, correct? Clearly. And here as well, the sine doesn't have a derivative equal to 0. So that means we can apply our theorem for this. As lambda gets larger and larger, both of these integrals are order 1 over lambda. Both of them are order 1 over lambda. That's what that generalized Riemann-Lebesgue lemma says. So the tails behave themselves. And Calvin pointed out this is not going to 0 very fast, but this is going to be fast enough for our purposes, so that we can basically neglect what's happening in the tails. That means, obviously, this integral is going to contribute more. Well, not obviously, but that's what we're going to find out. That this part of the integral is going to contribute the lion's share to the integration. But, you know, these ones are going to be lower order, which we can neglect. Now, let's expand about the point of stationary phase. And we'll do the sort of things we've always been doing, right? We recognize if you expand about this point, this is a bit like what we did with Laplace integrals of the second kind, right? So we said Laplace integral of the second kind, we look for a place where the derivative is 0. And then we did an expansion, but then we would either do a change of variables, or we would argue that we didn't have to do a change of variables. Okay, so we're gonna try to take the same inspiration. So let's expand t naught about the point, or sine about the point t naught. If you do that, then you get this power series expansion. Okay, the term that is linear in t minus pi over 2 goes away because obviously you have a derivative of sine being 0 there. Okay, so now I could think about replacing sine of t with, let's say, just this part. Remember I told you when we were doing Laplace integrations or Laplace integrals, if you did that, then you'll only ever get at most or at best the one order or one lowest order part of your asymptotic approximation. Okay, the leading order term, no corrections. So let's do that. Let's not worry about that because we already know that we're going to neglect these tails. We can't do much with those. They're going to be order 1 over lambda. So all we really care about is if we do this replacement here, we replace the sign with this function, that we don't incur any penalties or any errors which is larger than that. That's going to be the goal. Right now, we're just going to assume that that's exactly what happens. Okay, so we're going to assume that we can replace this guy with that power series expansion, making that a quadratic, and that we're still going to be asymptotic. Okay, we get this asymptotic. Now it's not exactly equal to it. We can only say at best it's going to be asymptotic. That's what we expect to find. We're also going to do, well, actually I did two things there. I did two things. I said lambda is large enough so that I can do two things. I'm going to replace this, and I'm going to increase the interval over, or I'm going to increase the size of my interval of integration, right? To go instead of pi by 2 minus epsilon to pi by 2 plus epsilon to minus infinity to plus infinity. And I don't have to really worry about centering it at pi over 2 because, you might say, well, you should probably center that. Well, that's just going to say that that's going to be pi over 2 minus infinity, and this one's going to be pi over 2 plus infinity. Okay. That's minus infinity, and this upper limit is therefore going to be plus infinity because we're just translating by a small amount. Okay, so that's the asymptotic approximation that I'm going to expect to be true when I make this this insertion, when I replace the sine of t by that, and I increase the interval of integration from finite to minus infinity to positive infinity. All right, so you probably shouldn't believe that that's true, but that's what happens. Okay, you should demand that you see a proof for this. All right, so let's continue in our calculation. So we have this integral. This is the integral of interest minus the tails, which we argued were big O of 1 over lambda. And I did this approximation, which we said we were going to do. But now we can integrate this guy exactly. We can do a change of variables on this. Bring out, there's one part of this integral which is a constant, right? I lambda times 1, that's just e to the I lambda. So that part can actually be brought out of the integration because it has no dependence on t. So that's where that guy comes from. And now I'm going to do a change of variables otherwise. I'm going to do the change of variables that sets s squared equals to 1/2 t minus pi over 2 squared. And then, of course, I shift my interval of integration again. All right, so after a change of variables, I hope you agree that I can get that. This is a Gaussian-like integral, but you've probably never seen this Gaussian. You may not have seen this Gaussian integral before. And the reason is because it's not a typical Gaussian because it has this minus, this square root of -1 in it, okay? But this is a perfectly nice integral, and I'm going to show you when we do contour integration in chapter 4 how to calculate this. And I know you're all excited about that. So has anyone done that calculation recently in complex analysis? Calvin, you did it?
I'm having complex analysis right now.
Okay, so you can probably believe this, right? You can do a contour integration to calculate this.
Or you can also make a change of variable, let u equals to square root of I times x.
Does that work?
Yeah, because you have square root of I, which is essentially e negative I power 4.
Okay,
That's just a square root of I.
right.
1 over square root of pi.
Okay, so maybe a simple change of variables gets you from, but when you do that though, you screw up your interval of integration, right? Your limits. I think you really do have to do a contour integral in this case. So how many of you have seen contour integrations before in the online or in person? Okay, few people have seen contour.
No, it doesn't affect because
I know why it doesn't, but actually you do.
radially symmetric.
Okay.
You just flip the y-axis back to the x-axis.
Okay, yeah, but you need a little something else. Okay. Okay, so some of you have seen contour integration, some of you haven't. Very important for physics and engineering. Any electrical engineers around? Any electrical? No. Very important for electrical engineering too. So I'm going to teach you a little bit about contour integration, and that's also going to help us with doing some other calculations that we want to do. In any case, this integral works out exactly. It's just everything that you see here. It's the square root of pi e to the minus I pi by 4. And of course, I can combine this guy together with this. All right. Now, this object here, therefore, if this asymptotic approximation is correct, is big O of lambda to the power minus 1/2. Okay, as lambda goes to infinity. Right? That's clearly true. What does it mean to be big O of something, right? It means I can take absolute value of this, bound it by a constant times actually in this case, this lambda that appears up in here doesn't give us any trouble. When I take the absolute value of that, I actually need to take the modulus of that. Then this has modulus of 1, and so it's pretty clearly going to be big O of this power of lambda to the minus 1/2. Okay. Okay, so this guy here, let's see. This guy here we're claiming is going to be big O of lambda to the minus 1/2 power. And these guys here, which we're going to drop, are big O of lambda to the minus 1 power. So they're bigger. Or no, they're smaller because the power of lambda is bigger in the negative sense. Okay, so now we have to finish up. We need to estimate the size of this error here. Okay, this is the integral that we started with. And this is the integral that we can actually calculate, right? We showed you can calculate this exactly, right? So what is the error incurred by doing the replacement of this integral with this guy, which we're hoping to be essentially the essence of the integration? Well, remember, we did two things. We dropped the tails. Okay, we dropped the tails, and we also, let's see, so in the theory of the stationary phase, what we're going to show is that we also made an error going from here to here, right? But what we're going to show in the method of stationary phase is that error that we make is big O of lambda, 1 over lambda as well. Okay, so the two errors that we made are in sum total going to be at worst big O of lambda to the minus 1. And we just showed that if you keep the main thing, then this is that term here. So if you put all that together, then what you show is that the leading order asymptotic approximation for the Bessel function, or at least this pre-Bessel function, is just going to be this guy here. Okay, this 1 over, so this guy is like order of lambda to the minus 1/2 plus this order of lambda to the minus 1 correction. Okay, so this is the essence term here. If you can say that, which is just this, then we can prove that I is asymptotic to this value. Okay, so in other words, as lambda gets large, this is essentially what the function is going to look like. Now, how do you guys remember how to show something like this? What does this mean? What is the definition of this? Okay, what do we need? What would we need to show to prove that? I would need to show that I minus or I of lambda minus this approximation 2 by pi lambda. Don't need all that. Smaller. E to the I lambda minus pi by 4. So how do I show that this is asymptotic? Well, I need to show that this is what? Little o of something. Do you guys remember what it is?
So,
Yeah, it would just be all of this. Okay. All of that. That's my G. This was my F, that's my G and my S. But really the essence of this guy in terms of its asymptotic nature is just going to be little o of lambda to the minus 1/2 power as lambda goes to infinity. So that's really all I have to show. But if this is true, right, then I have it, because the remainder term, which is this bit here, is big O of lambda to the minus 1. And if I multiply lambda to the minus 1 times lambda to the 1/2, and I take lambda to infinity, this guy goes to 0. Okay. You see why? Because this is just going to be 1 over lambda to the 1/2. Okay. Now, you might have to really sit down with a piece of paper and convince yourself that that's what's going on. This might be going over your head and way too fast, but if you go back to the definition, say, what is it do I really have to show? Why does this work out? Why is this true? Then you'll see that it comes together. Let me conclude, though, at least with this part. So if I can show this, I just take the real part of that, and that gives me the asymptotic expansion or the asymptotic approximation for the Bessel function. So it says that the Bessel function, and obviously when I take the real part of this whole function, then I just need the cosine bit of this, right? In the Euler formula, just the cosine bit. So I get the 0th order Bessel function as lambda goes to infinity is asymptotic to this prefactor, which is order lambda to the minus 1/2, times cosine lambda to the lambda minus pi over 4. All right. So how good of an approximation is that? So here's a plot of the Bessel function according to Mathematica. It's the blue curve. And our asymptotic approximation, which has to blow up to infinity, right? As in this case, it's x. So normally it should be lambda. I guess I really want this to be lambda at this point. So I might go back and change it. But in any case, as x here goes to 0, this guy has to blow up to infinity because we have a 1 over x square root there. Notice that after about lambda, remember we commonly think that to get good asymptotic approximations, we probably need to go to lambda large, or at least grab a couple of terms and take lambda large, right? This is the 0th order correct, or the leading order approximation with no corrections. And look, to lambda equals 4 by the eyeball norm, these two things are exactly the same. If you go out to lambda equals 8, you definitely can't tell a difference. Basically, this function, this Bessel function, is this function for all intents and purposes for x or lambda greater than 6, right? They really lie on top of each other. So Calvin, why do this part, right? Asymptotic expansion. If you need to know what the Bessel function looks like for large arguments, then you don't want to do an integration. You just want to say, for large arguments, I know it's basically this prefactor 1 over square root x times cosine x minus pi by 4. Almost perfectly. So this is pretty impressive, I think. Okay, now, all right, so let's review what the method of stationary phase is in at least from our heuristic level. All right, so we've got our Fourier integral. We identify what f is and what psi is. We need to find out if there's a point of stationary phase. So here we're going to assume that there's a single stationary phase point, T naught, which exists in the middle of the interval. Okay, somewhere deep in the jungle, right? Not at the endpoints A or B, but in the middle. Okay. And we're going to assume that psi prime of T naught is 0. That's a stationary phase point. And psi prime of T, this should be T naught here. No, this is correct. And psi prime of T is not equal to 0 for any T value that's other than that point of stationary phase. So that's correct. But now what I'm going to assume about the second derivative at T naught, I'm going to assume that that's a positive number, just so we can make some progress here. Now you'll notice that when we calculate the Bessel function, there was no f function floating around at all. All right, so we do have to modify our work if there's an amplitude function, right? Multiplying this oscillatory part. Okay, so psi double prime is equal to alpha, which is positive. So we argue that you can write I of lambda equal to something like this, an integral which just surrounds the point of stationary phase and these two integral tails. Let's see. I think that this is a typo here, right? It's just this guy plus that. We don't want that. That wouldn't make much sense. Just the integral around the point of stationary phase, and it's two tails. And that's clearly wrong. Okay. Just this part's the wrong part. Okay. Next, we're going to argue that the tails are going to be treated with the Riemann-Lebesgue lemma. Eliminate this guy. I'm eliminating references to theorems because it makes sense in the book, but not in the notes, because in the notes, Beamer doesn't add a counter for the theorems or propositions. Okay, so by the generalized Riemann-Lebesgue lemma, we can argue that these two guys, because f is well behaved and this guy is well behaved in this interval, it doesn't have a point of stationary phase. Okay, it has no derivatives equal to 0. So the generalized Riemann-Lebesgue lemma can take care of that and says that those tails are both going to be order big O lambda to the -1. Okay. Then we're going to zoom in on this integral around the point of stationary phase. We're going to argue that that guy, if I do some manipulations with it, is going to contribute at most order big O lambda to the -1/2 power. So that's going to be the dominant contribution. And here's how. So first I start out by doing the power series approximation of this guy up to the second order, right? There is that, up to second order. Then I argue that this guy can just be taken out. That was the f of t. I'm just going to argue, well, that's basically just going to be, these intervals can be made small enough. This is a continuous function. But basically, this guy is just going to contribute its value at the point of stationary phase. Okay? So I'm going to bring it out. There's also a constant term here, which doesn't depend on t. That can be brought out as well. And then we're going to puff up this interval of integration. We integrate this integral exactly, and that gives us that contribution that we mentioned before, square root of pi e to the I pi by 4. And that gives us in total this contribution here for this interval, or for this integral. We made a couple of corrections to that, but this should hold true. Now, basically, this is the main part, or the main contributing part of our analysis here. Okay. And we argue that what we discarded here, what we added, contributes at best order big O lambda to the -1 power. And since this is lambda to the power -1/2, then this guy is going to dominate. So basically we're arguing that, and that's going to tell us essentially to leading order, I of lambda is approximated by that. So that's the general form of the method of stationary phase. Okay, we don't have time now to go through the proof of that. The proof is contained in the next few slides. Some of you won't care to see the proof. Some of you might run from the proof, but we will do that next time. We'll go through the rigorous proof that this actually holds. Okay, and you can already see how well it does using Bessel function as an example. So this, even just getting a leading order term can be quite useful in approximations. All right, so I'm going to stop there. If you have any questions, you can come up afterwards. You can send a note in the chat. But I'm going to sign off for now, and I will see you guys. If you want to show up for office hour, tomorrow there's an office hour from 10 to 11, so I'll see you there if you want to come to office hour. It's via Zoom, and you can find the Zoom link in Canvas. But otherwise, I'll see you guys at the next meeting on Tuesday. Have a nice day.